the first chapter 9. There's 2 topics in this. And the first one we're going to look at is Introduction to Sampling Distributions, which we did yesterday. Get you some more jargon. If you hear the word parameter being used, then you are talking about a number in a population. So a parameter is basically just some number that represents some useful information. So a parameter could be the mean of the population, standard deviation. It can also be a thing called proportion. So I don't think I've mentioned the proportion one. We have a very simple situation when we talk about proportion. If you ask everybody in the population a question and they're only allowed to say yes or no, then the percentage of people who say yes is typically called P. So you might go and ask everybody in your population, have you been to France? And 12% said yes. Or are you over 6 feet tall? 8% said yes. So the proportion P is typically attributed to some question where there's a yes or no answer. And when you write down the P, you typically write the answer as a decimal. So you asked everybody in the population a question like something you could say yes or no to, like, are you going to watch television tonight? And they said yes. And that would be your proportion. Now, a statistic is basically the same kind of numbers. They represent the same kind of information that the population does, but a statistic comes from a sample. That's the main difference. So when you use a sample, the sample statistic for the mean is called X bar. For the standard deviation, it's typically called S. And the sample proportion, it's this little guy here, which you say out loud as P hat, because it looks like it's got a hat on it, I guess. So suppose I was interested in, for instance, what percentage of people in Olympic College, right, have been to France, right? And I would collect a sample. So let's do that sample. It shouldn't be too long to pick up. Right, there's 1, 2, 3, 4, 5, 10, 15, 20. There are 22 of you in this class, including me. And if you want to vote, so we'll assume that you're all going to tell the truth and that you will vote. You go down to the little reactions guy and you will say, thumbs up, I've been to France. So how many have been to France? One, two. So the answer to P hat was 2 out of 22. And
Professor
that would
Robertson?
be, yes.
Can you put back up what you just had for a few more seconds? Because I didn't write it all down.
Yeah, that's fine. I'll be adding to it on the other side. So we've got 2 things going, right? So 2 out of 22, we would call P hat, the proportion who've been to France, as of Olympic college students at least, is 0.09. That's to 2 decimal places. Now, I don't know what the real answer is. I'm lying here, really. The population here is OC students. And I think you lot are a fair representation of OC students. So I don't think that would be unlikely. And let's just pretend that the real answer was that one. So the population parameter P would be 0.07. The sample statistic P hat would be 0.9. So we're just getting you used to the language. You say population parameter P, sample statistic P hat. Now, do you see that they're trying to measure the same thing? This is the truth, right? And this is my sample estimate, really, assuming that I told the truth when I said it was 7%. And the main job of samples is to try and predict these guys. We very rarely ever try and predict the standard deviation of a population. because it's not that interesting. But we do want to know what the mean and what the population proportion is, right? That parameter, because they're very often very important things to do. Every election that I can think of, don't they try and find out who's going to win it before it's even taken place? Right? They do polls. And now what a poll does is you ask 1,000, typically it's about 1,000, random sample voters, who they're going to vote for, Republican or Democrat. And that number can then be your estimate for what the entire population who would vote would be. And that's a very useful thing to know. So are we comfortable with the terminology? If you see mu, sigma, or p, you know it's to do with a population, and you know what you're measuring. When you see mu, you're measuring the mean of the population. If you see a sigma, you know you're measuring the standard deviation of every single person in the population. And the population proportion guy P, that's the percentage of people who said yes to whatever that question happens to be. So that's kind of vague, isn't it? Because, you know, is your favorite color red? Yes or no, right? Could be any question as long as you can phrase it with a yes or no reply. And if you're doing statistics, basically there's a kind of mirror image going on here. For every population parameter, there's going to be a sample statistic that tries to measure it. X bar for the mean, S for the standard deviation, and sample proportion, P hat. So far, so good? Right. Now, if I can do this without screwing zoom up, been causing me all sorts of issues lately. Okay. Got a number of questions here. I wish I would stop doing that. Stop giving me the answers. Distracts the heck out of me. Although that means I'll probably get them wrong, but never mind. There we go. Can I make this bigger? Probably. Okay, this is introduction to sampling distributions. And move this over a little bit. Too big. Okay, shrink it one last unit. There we go. In each situation, explain whether the number, the value given in bold print, which I'm assuming in my case means the red number, is a statistic or a parameter. So you can imagine these homework questions are going to be pretty quick, right? They give you a quick story about some information they collected, and that number that's highlighted here in red, is that number representing a sample or a population? If it's a sample, it's a statistic, and if it's a parameter, it's a population. So just by looking at these choices, without even looking at the question, right? Isn't that one always going to be wrong? And the reason it's always going to be wrong is if you're a statistic, you can't be a population number, right? And in the same vein, won't that last one always be wrong? Right. So in this story then, 1,000 adults, 73% thought that you should increase the penalties for drunk driving. That is clearly a sample grade, so it's a statistic. And that's pretty much it. In the year 2010, there was a census. The US Census Bureau found that the median age of Americans was 37.2. Is that a statistic or is that a parameter?
Parameter.
Right. The minute you see the word census, it's just another way of saying we asked everybody, or within practical things. Now, is it a parameter because it's a population value, or is that a parameter because it's a sample value? Got one right. If it's a parameter, it better be from a population. If it's a statistic, It better be from a sample. If you can remember that, you've already eliminated half the kinds of questions that you would do. Let's just randomly scan it through the next one. Some stockholders want to know whether the mean salary for male employees in a company is higher than the mean salary for the female employees. The company allows them access to the salary information of all their employees. And that happens to be 100 males and 100 females. And the males are 53 and the females are 5,500. Interesting information. Are these numbers statistics or parameters? I see your mouth moving, but I didn't hear what you said, David. I couldn't pick up what you agreed. How do you know it's a parameter? What in the information here? I mean, I could almost pick one word, just one word that kind of tells me. Yeah.
All.
You see it there? Right. Now, if they said, you know, we're a big company, so we took a random sample of 1,000 employees and the average wage was, then that would have been a sample, right? If they'd said we took a census, that would be a parameter, right? That's everybody. Or we looked at all of them, that would be another way of saying that. That would also be included. Now, in this question, P hat or P, what is the correct label, right? The correct thing you should call this story. Now, remember, P is a population number, right? The information you got came from everybody, and a P hat came from a sample. So when you read the story, try and decide, is this everybody or is this just a sample? So the proportion that smokes in a randomly selected sample of 400 students. Would you agree that bit there pretty much decides the answer? Is it not a sample? And when it's a sample, don't you use P hat? And it's P hat because it's a sample. The proportion that smoke amongst all students, oh, there's our fancy word, all. Do you see that's going to be a population number now, right? You've asked everybody. And since it's a population number, it's a P. And P's always go with population, and P hats always go with samples, right? You'll never have a sample proportion called P. They're always called P hat. You will never have a population proportion called P hat. They're always called P. A different type of question here. Here's our story. In a random sample of 300 parents in a school district, 124 of them supported a controversial new education program. The purpose of the survey was to estimate the proportions of all the parents in that school district. So they kind of wanted to get a feel for what did everybody think, right? Which is pretty common for these types of questions. Now, what is the research question of interest in this survey? And they give you 5 different, you know, dump kind of thing, right? Which one of those 5 is the research question that you're interested in answering? One, 2, 3, 4, or 5. Which dot would be what you're interested in getting information about?
3.
And you're using that sample to try and obtain it.
Would it be 3?
It would.
Okay.
What was the clues in this one?
Proportion.
Yeah, definitely.
Parent, yeah.
Yeah, it might have helped if they said what proportion of all parents. I think we're just assuming that the word all is implied in the way they phrased it. Which one of these symbols would you use for a sample proportion?
P hat.
That one. Won't let you read the others. It's very similar questions, so I'll just go by that one. Okay, question 8. I wonder if I can make this bigger, because I know that some of your screens are not as big as mine. Nah, shooting space. Okay, that's as good as I'm going to get. Okay, this question number 8 says, consider a situation in which a sample of 100 SAT scores is taken from a population of all people who took the test in a given year. So the people who run the SAT are always on the lookout for fairness, for want of a better word. Don't you not want an SAT from this year to be distinctly harder to get a good score than last year, right? You want it to be pretty much the same every year. Now, they make up questions, but you know, isn't the problem with questions is, you know, it's quite subjective sometimes how difficult a particular question is. You agree? You might think it's an okay question, and then a lot of people find the wording awkward, or you know, it's a hard question. So what they do is they keep an eye on the averages and they do samples. In fact, very often they do test runs, which means they get volunteers and they do SAT questions. You know, typically college students get paid to do it. And what they get from that is a kind of idea of how difficult a question is by how many people got it right. And then they can balance it. So that kind of thing is happening here. So in this particular story, right, there's 100 of them. And which would be the more spread out? A sampling distribution of the mean of the 100 SAT scores, or a histogram of 100 SAT scores reported in just one sample. Now, the way they phrase that is a pain in the butt, so let me rephrase it, I hope, in a little bit better way. Imagine you took, what was the number? You took 100 SAT people, right? And you collected their SAT scores. Can you imagine you make a histogram like that, right? Each one of these is like one particular score, might be. That would be what it would look like. Now, if you took 100 and then you averaged it out, and then you took another sample of 100, right? And you averaged it out. Remember, we did this kind of the last day. What you get is called the sampling distribution. Remember the sampling distribution? Now, for 100 people, it's pretty spread out. When you average them out, the sampling distribution, it's much tighter. In fact, I believe I even told you what the standard and deviation is, right? Wasn't the standard deviation essentially sigma over the square root of n? So what that is telling me here is that if you do 100 people and you average them out and you do it lots and lots of time, you get a shorter, a smaller variation. So that question there was asking about the sampling distribution would have a smaller standard deviation than just 100 raw data would. And there's 5 choices there, and one of those basically ends up being what I just said. And that is pretty much the end of that particular question or section. It was mostly about jargon words. So get used to parameters and population and statistics and samples. And now we're going to look at this fella. Sampling distribution again. But we're going to do it for the proportion fella. So here's my little story. I'm interested in United States of America, that's going to be my population. And the thing I'm interested in is P, which is the proportion have been to Canada. So what proportion of Americans have been to Canada, right? Haven't any idea why I want to know that. I just felt like it was an interesting thing to find out. So how do we do it? Well, just like we did last time. Couldn't I just ask every single person in America, have you been to Canada? And hopefully they tell me the truth, right? And if I did that, it would be a census. And let's just pretend that the answer, let's pretend. Let's pretend that the answer is 12%. That is a population parameter, right? 12% of Americans, somehow or other, I managed to get enough money off Bill Gates and I conducted a big census and I came up with the answer 12%. Well, we know that that's probably never going to happen. Nobody's going to pay me, millions. It would cost millions to do that, by the way. So what we do is we get a sample, don't we? And it's going to be a random sample. And to keep my numbers nice and simple, I ask 100 Americans, right? A nice, simple random sample of 100 Americans. I ask them, have you ever been to Canada? And I got the answer, 11%. Remember the argument we used last time? That's not bad, isn't it? You don't expect to get a perfect answer when you do 100, right? The best you can hope for is that you get something that's close to the answer, right? That's what a sample does. It's an estimate of the real answer. And I'm calling this guy P1. And then I did it again. And just like I said last time, couldn't the next time I do it, couldn't it be 12? And then I do it a third time. And when I do it a third time, it ended up being 14. And can you imagine I just kept on taking lots and lots of random samples, all of size 100. And when you do that, you create what's called a sampling distribution.
Question, P1, yes. P2, P3, do those need to be P hats?
Thank you. I did make that mistake, yes.
Okay.
Because it's a sample, I should have called them P hat. I'm getting old. Now, the sampling distribution will look like that. And right in the middle, the theory tells us that you get 0.12. And just like a normal distribution, it's got that nice bell-shaped thing. And would it be nice if we could find what the standard deviation would be? And there is a formula for calculating the standard deviation. And the standard deviation is given by this guy. P, a guy I haven't talked about yet, Q over N. So let's tell you who Q is. If P is the percentage, is the percentage of people who said yes to your question, Q is the percentage of people, or in this case, proportion of people who said no. Okay, so if I tell you P is 0.1, don't you know Q is 0.9? There aren't any don't knows allowed, right? We simplified the situation down. So in this particular question, we have a p-value of 0.12, a q-value of 0.88, and a sample size of 100. So I'll go to my calculator and I'll do the square root of 0.12 times 0.88, and I'll divide that by 100. And the answer I get is 0.03, at least to 2 decimal places, which means 0.15, 0.18, 0.21, and going on the other side, 0.90603. That's what the theoretical sampling distribution would look like. Unfortunately, you can't really calculate that guy in real life, because to calculate that guy in real life, don't you need to know the population parameter P and Q? Now, if I knew what they were, why am I spending time getting a sample, right? So kind of common sense is that you don't know that number. So what's the best you can do? Well, we can estimate it. And when you estimate it, you call it the SE of P hat. It's called the standard error of P hat. And of course, it has a formula. Oh, I just realized something. For some reason, the book does not use capital letters. They call it little s, little e, just in case you read it, you wonder what the heck's going on. It's the same thing as that. I just forgot that they do little letters. And it has a formula. What do you think the formula for the estimated standard deviation? That's basically what the standard error is. It's the estimated standard deviation, right? What do you think the formula for it would be based on what you can see over here? Any ideas? I can't hand it to you in a plate anymore, right? I'm pointing at it. How would we be able to adapt this to take into account that we only have p hats to play with?
It would be the same thing, but with the p hat instead of p.
Yes. It's that guy. In the big scheme of things, if that's the only thing you've got to play with, isn't that the musical instrument you have to blow? Right? I only know P hat. I don't know P. If I knew P, I wouldn't be doing this in the first place, right? My problem would have been solved. So for some reason, I went red a lot. Let's assume then that I did it again and I collected a sample, and I'm going to change my sample up a bit. I got 1,000 people. And when I did the 1,000 people, the answer I got was 11%. So 11% of the people I asked have been to Canada. And I would like to take that piece of information and see if I can create the sampling distribution, right? This picture. Well, I already know that the best I can guesstimate is that this is 0.11. And now I'm going to get my standard error of p hat, which is the square root of p hat q hat over n. So in this case, it's going to be 0.11, 0.89 all over 1,000. Let's see what that looks like. If you do the square root of 0.11 and you multiply it by 0.89 and you divide that by 1,000, the answer I get is 0.01 to 2 decimal places. So 0.12, 0.13, 0.14, 0.10, 0.09, and 0.08. So this fella here is my best estimate of what the real answer would look like, right? In any given case, right? This fella here. Now, how do I use this to help me make a prediction? Well, I could simply just say my best estimate is 11% of Americans have been to Canada. But wouldn't it be better if I could do what's called a confidence interval, where I gave an interval, a range of values that I am 90 or 95 or 99% confident is correct. And I'm going to use a guy that's been a while since we've used this guy. What percentage of data is between 2 standard deviations of the mean? 95? So if I wanted to give you a 95% confidence interval, wouldn't I just take the mean? Think of p hat as just the mean, right? It's the average answer that you would get, p hat. And I'd add or subtract 2 of these guys, essentially 2 standard errors. And in this case, I get 0.11, give or take that guy. And that gives me 0.09, and it goes all the way up to 0.13. And as percentages, couldn't I say something along these lines? I am 95% confident that the real answer for all Americans who've been to Canada is somewhere between 9 and 13%. Now, I'm not making any value judgment on which of those numbers is the most likely. It could be as low as 9, it could be as high as 13, it could be 12.2, it could be 9.7. So when you do a confidence interval, the guy in the middle, the p hat, is no more valid an estimate as the 13% is or the 9. In other words, every single one of the numbers in that interval is just as likely to have been the real answer, right, as any of the other numbers. But okay, I cheated a little bit, but it was right. Doesn't that actually match reality, at least my pretend reality? Isn't the real answer 12% inside this 95% confidence interval? Suppose I wanted to be 99% confident. Then wouldn't I just do 3 standard deviations, which would be between 8% and 14%? Now, if you're giving someone an estimate on what you believe the true value for P is, would you agree that it's better to give them an interval with some kind of confidence attached to it than just say, my best guess is 11%? It could be a really bad guess. It could be a really good guess. You decide. Isn't it a little bit more specific to do confidence intervals? Now, right now, we are only going to do the 1, 2, 3. I don't like 1, but they do ask it. See if they did 1 standard deviation away from the mean, wouldn't that be a 68% confidence interval? And a couple of reasons I don't like that. If you do a 68% confidence interval, doesn't that mean 1 out of 3 times you're wrong? I don't like those odds. I like 95, I like 99. Later on, you'll find we can do 90% and 99% as well. We just have to tweak this number. It's got different values for different situations. Any questions about this, or is so far so good? So let's do another pretend one. At this time, I'm going to use you lot, and I don't know what the real answer is. So in a way, we're going to hopefully find out what the real answer is. Back to front way of saying it, but whatever. So get ready to vote on this one. Has anybody got an interesting question they'd like to know about the class, but it can't be too sensitive, right? We don't want to ask them things that they feel uncomfortable about. Could be like, do you like ice cream? It just has to say yes or no to it. I mean, I could make one up, but it'd be fun if you did. Anything you want to know about this class?
Apple juice or orange juice?
Okay, so apple juice or orange juice? How am I going to phrase that? You are only allowed to drink one of the following two. Would you choose apple juice? Yes or no? Okay, so would you do apple juice? Yes. So I'll need the little icons because I can't see all your pictures. So would you choose apple juice? 1, 2, 3, 4, 5, 6. Good grief, everybody. Well, not me. 1, 2, 3, 4, 5, 6, 7, 8. I think it's 8. We pretend it is. So you are going to represent everybody in America. So you are going to represent the battle between apple juice and orange juice. I bet you there's been a version of this where you did Coca-Cola and Pepsi. I'm sure there's been one like that, right? So we're doing the apple juice, orange juice one, and we are going to look at this percentage and see what we get. So I'm going to turn it into a decimal. And in this case, I think I'll be a little bit more accurate. 0.364. About 36.4% of you prefer apple juice over orange juice. Well, I would like a 95% confidence interval, right, based on that. So I need to calculate the standard error of p hat. So it's going to be the square root of p hat, q hat over n, right? That's the formula for that guy. That's going to become a 0.364, that's p hat. Q hat is going to be 0.636. Yep. And there's only 22 of us. And so we will now go and do the square root of 0.364 times 0.636. Going to divide it by 22. And the answer I get is 103, which is about 10.3%. I could, but I don't want to because I'm running short of time. Couldn't I create one of these, Vishpa? I apologize. You didn't see any of that, did you? No. 22, 8 out of 22 people, 0.364. We're going to do a 95% confidence interval. To do that, I need to know the standard error of the p hat, and it's this fella here. And so for a 95% confidence interval, it's p hat plus or minus 2 standard errors. So it's 0.364, give or take 2 lots of this. So that's 0.364, give or take 0.206. So that's 0.364, take away that number, 0.206. And on the lower end, then we got 0.158. And then if I go 0.364 and I add 0.206, at the upper end, we get 0.57. And I prefer percentages. So we are using our sample, and we are 95% confident that somewhere between 16 and 57% of Americans prefer apple juice over orange juice. First thing that strikes me is, isn't that interval huge? The real answer could be anywhere from 16 to 57. But there's a very good reason why that interval is so big. A very practical reason. Why do you think it's so big?
Our sample size?
Yeah. You know, big sample sizes, small standard error, the interval gets narrower, doesn't it? But if the standard error was only 2%, wouldn't we shrink it down to a nice compact window that we'd be pretty good at? So the only way of getting good data is ask more people. That's the bottom line. If you don't like the data that you've got, you know, if it's too vague, the only way to fix it is start again and ask, ask 10 times more people than you asked the first time, you know, make it big, make it better. Do you see this as a process that we use in many ways? Isn't this the kind of standard statistical process for estimating things? I wonder how many Americans are going to vote Democrat in Bremerton's next election, right? I wonder if Pepsi's more popular than Coca-Cola. Right? I wonder how many people are intending to go on holiday to another country next year. Right? Any kind of question you want to ask that's got a proportion, right? A yes, no to it. This is how you would do it. The trick is big sample and make sure your sample is truly random or as random as you can make it, right? Now, there are a couple of restrictions to using this method. The major one is it should always be a simple random sample. It's sometimes called, borrowed from computing, garbage in, garbage out. If I was interested in people who are intending to go to a foreign country next year, do you think it would be a bad idea if I just asked airline pilots? Would you agree they're not a fair representation of Americans? And I would probably get a very inflated answer, right? Hey, 82% of you are going to go to a foreign country in the next year, right? Okay. So simple random sample. We typically assume that that's the case, so you don't need to test for it. Second thing that causes problems is the sample size is too small. And you might think, well, that's like measuring a piece of string. I think 100 is too small, but Cheyenne thinks it has to be 50 before it's too small, right? That's kind of vague, isn't it? So there is a test for being too small. Surprising, but there is. N times P hat and N times Q hat have to be greater than or equal to 10. That's it. Now, that does mean that a sample size can be too small, even if it's a big sample. Imagine I asked 1,000 people, have you ever had a rare version of cancer? And the answer I got was only 2 people. Right? So it would end up being 0.002. If I did NP hat here, it's basically the number of people who say yes. That's what NP hat is calculating. In this case here, wouldn't it only be 2 people? And we would consider that too small a sample size because it fails under here. Even though those sample size is 1,000, it's not just the sample size, but it's the people who said yes inside that sample size, which is much more important. Now, I could have quite a small sample, 50, and P hat ended up being 20. Obviously, Q hat would be the rest. Can you see in this case, the NP hat, oh, I should be putting in decimals there, right? 0.4 and 0.6, right? Although that is quite a small sample, when you multiply it, don't you get an answer that's bigger than 10? What that tells us is that this, you can use the technique and it will give you valid answers, provided number 1 is true, that you truly did have a simple random sample. The interval would be huge, agree? If you did a sample size of 50, your answer might be the number of people who like orange juice, like apple juice, is somewhere between 5 and 95%. You know, it'd be some ridiculously huge interval, but it's doable, right? You could still do the calculations and you could still get an interval. On the other hand, with a rare form of cancer, you couldn't do, according to the theory, you couldn't do this technique because it fails under the sample size rule. I think that is a very nice place to finish.